So I didn't cover the ideal gas law in lecture this week. I want to just take a moment here to connect sort of previous ways that you've probably seen the ideal gas law to the way it appears in our textbook. The way I'm sure most of you have seen the ideal gas law is that pressure times volume is related to the number of moles of the gas times a constant R times the temperature. Now it's important to note that the temperature is in SI units in degrees Kelvin, not in Celsius and so on. It's got to be relative to absolute zero. The other thing I'll note is that this constant, R, is a universal constant. And because of that, and it has a specific value, 8 point something or another, I'm going to denote that with a subscript U. So to rewrite that then, we have PV is equal to the number of moles times our universal constant, R, times temperature. Now in the form that we work in the book, we are going to convert things to density. And so the density, we know density is going to be equal to the mass per volume. And the way we're going to write the mass is to say that the mass is equal to the number of moles times the molecular weight. So that script M, poor script M, but you get the point, is the molecular mass, I should say. Mass per mole. So what that allows me to do is to rewrite the density, say, in terms of rho is equal to N times the molecular mass times divided by the volume, or I can rearrange this to say N is equal to rho times the volume, that's the density, times the volume divided by molecular mass. Now I'm going to take that relationship and I'm going to substitute that into our original ideal gas law for N. So what I get is that pressure times volume, that's a poor P. Let me just rewrite this. P times volume is equal to density times volume divided by molecular mass times our universal constant times the temperature. Well, this can now obviously be simplified. We have volume on both sides. I'm just going to cancel that, cancel out those volumes, and rewrite this as P is equal to the fluid density times, now I'm going to group our universal constant with the molecular mass times temperature. And temperature in degrees Kelvin. Now I define this ratio of universal constant to the molecular mass as a new constant R, which is now gas specific, and so I get that P is equal to rho RT, and R then becomes a gas specific constant. So that's the connection between the form of the ideal gas law that appears in the book and the form of the ideal gas law that you're probably more accustomed to. And they are in fact equivalent, where we've made this translation from thinking of moles to thinking of density, which is more convenient for the way we're thinking about fluid mechanics.